Picture this. You wake on a Monday morning, the week stretching before you in its predictable, orderly fashion. You perform the small, mundane ritual of checking your weight. The number is what it always is, a fixed point in your personal universe. It is a fact of your physical being, as unchanging as your height or the color of your eyes. The week unfolds. Meals are eaten, miles are walked, life is lived. Come Friday morning, you step onto the same scale, in the same spot, with the same body. The digital readout flickers and settles on a number. But this number is not just different, it is an impossibility. It tells you that you are not slightly lighter, not a pound or two down, but 100 times lighter. The solely ground of reality beneath your feet doesn't just shift, it evaporates. The instrument is not broken. If you're as captivated by this as I am, I want you along for every step of this investigation. Go ahead and like and subscribe right now, so you catch every development as this story continues to unfold. Leave a comment telling me where you're watching from, what time zone you're in, and whether you think we're being told everything about what's really happening up there. Because this is where the story splits between what we're told and what the data screams. Your eyes are not deceiving you. Two mutually exclusive truths now occupy the same space in your mind, and the cognitive dissonance is a physical ache, this precise, vertiginous sensation, the total collapse of a fundamental assumption about measurement, mass, and the very consistency of reality is exactly what has just gripped the field of astronomy. This is not about a body on a scale. This is about a body in the void. This is the story of the interstellar object designated 3I Atlas, and the quiet, devastating paper published in December of 2025 that did not update our understanding. It annihilated it. For nearly a full year, the narrative surrounding 3I Atlas was one of monumental discovery. From the moment its hyperbolic orbit was confirmed, marking it as a traveler from another star, it was a celebrity. Telescopes across the globe and in space swiveled to track its passage. The story they told, the story we all consumed, was one of imposing scale. This was no fleeting snowball, no pebble tossed by galactic tides. Data converged to paint a portrait of a cosmic sovereign, a roughly spherical object 5 kilometers in diameter, composed of ancient ice and dust, with a calculated mass of approximately 33 trillion kilograms. To grasp that scale, imagine the weight of a small moon, a fragment of a world, cruising through our solar system as a silent ambassador from a stellar nursery we will never see. An object of that immensity possesses gravitational presence. It moves according to the clean, predictable lines of celestial mechanics, its path dictated by the sun's overpowering pull and the gentle nudges of planets. Forces like the pressure of sunlight or the faint push of escaping gases are meaningless to it. They are breezes against a mountain. This was the comfortable, awe-inspiring consensus. It was the headline, the textbook entry in the making, the confident assertion in every press release from every major observatory. 3I Atlas was a giant. It was a fact. Then, on December 11, 2025, a study authored by researchers Forbes and Butler appeared on the Arxiv preprint server. In the dry, technical language of astrophysics, it performed a kind of academic execution. It did not suggest minor refinements to the giant's dimensions. It did not propose tweaks to the density estimate. With methodical, devastating logic, it decapitated the giant entirely. The new analysis, incorporating ultra-precise positional data and groundbreaking infrared spectroscopy from the James Webb Space Telescope, arrived at a conclusion so divergent it felt like a mistake. The mass of 3I Atlas, according to Forbes and Butler, was not 33 trillion kilograms. It was 260 billion kilograms. Pause. Read that again. Let the sheer magnitude of that correction wallow in your mind. This is not a matter of being 10% off, or even 50. This is not a recalibration. This is a wholesale reinvention. It represents a reduction of 99.2% in object losing more than 99% of its supposed mass between one dataset and the next. The discrepancy is not a rounding error. It is an abyss. These two numbers, 33 trillion and 260 billion, do not represent different measurements of the same entity. They describe two entirely different physical objects. They are incompatible truths. One truth describes a slow, ponderous monarch of the deep, an object so massive it shrugs off the petty forces of its environment with imperious indifference. The other truth describes a cosmic feather, a fragile, lightweight assemblage so insubstantial that it must be swayed and buffeted by every minor influence. its path a delicate dance between gravity and a dozen other tiny pushes. The term revision is laughably inadequate here. Revisions are for correcting a misprint, for incorporating a new, sharper photograph. What happened with 3i Atlas is of another category entirely. This is two teams of impeccably credentialed, meticulous scientists using state-of-the-art technology, following rigorous methodology, and publishing in good faith, looking at the same speck of light against the star field and arriving at conclusions that are mathematically and physically mutually exclusive. One of these carefully constructed realities is a mirage, and here is where the hook sinks in past the skin, where the story transcends a scientific disagreement and becomes a genuine mystery. Both datasets are, in their own frames of reference, correct, and if that is true, then the bedrock principles we use to interpret motion in space, the very calculus that guided Voyager to the stars and maps the future paths of asteroids, contains a fundamental flaw we have never perceived. Our understanding is not slightly off, it is catastrophically incomplete. The reaction within the astronomy community has been telling. There is no outrage, no loud dismissal. Instead, a profound, quiet confusion has settled, the kind that blooms when language fails. I have spoken to researchers who shrug, not with indifference, but with the fatigue of the baffled. They call it a physics paradox, a sterile technical phrase that masks a thrilling and terrifying admission. We have no idea what is happening here, because the logic is inescapable and circular. If the lightweight December model is the true 3i Atlas, then the earlier months of observation become a phantom record. They captured an object behaving with the inertial stability of a giant, an impossibility for something so slight. Conversely, if the earlier, massive model is truth, then the December data is an illusion, measuring forces and accelerations that have no business existing. You are trapped. If you accept both sets of observations as valid, as each team passionately argues they are, then you must discard a foundational pillar of physics, that an object's mass is a single, immutable property that reveals itself consistently through its motion. 3i Atlas did not metamorphose between August and December. The universe's rules, as we have written them, did. We are now collectively staring into a crack in reality, trying to decide which reflection to trust. The 5-kilometer Goliath that captivated the world, or the 1-kilometer imposter that materialized in the December data, possessing a mere 1% of the expected mass, and somehow deceiving the most advanced telescopes ever built. But this is the thought that transforms intrigue into obsession, the notion that turns a puzzle into a potential revolution. Genuine enduring paradoxes do not exist in nature. They exist in human comprehension. A paradox is a flashing red sign on the road of discovery that reads, "Your map no longer matches the territory." Every historical instance where we have confronted a true paradox, the precession of Mercury's orbit inexplicable under Newton, the ultraviolet catastrophe that shattered classical physics, the wave-particle duality that defies common sense, the resolution has never been a minor adjustment. It has always been a tectonic shift in perspective, a demolition of settled knowledge and the construction of a new, broader, stranger framework. So the urgent, thrilling question is, which assumption are we about to watch crumble? Is it our model of comet composition and structure, our ideas about how mass is distributed in objects formed in alien solar systems? Or is it something more profound, more disturbing, a flaw in the very methodology we use to deduce the nature of distant things from the faint, ghostly signals they send us? The December paper was a challenge thrown down not merely to a statistic, but to the entire epistemological framework of remote observation. It challenged how we know what we know about that which we can never touch. And if that framework has a hidden fracture, then 3i Atlas is not an outlier. It is the first thread we have pulled in a vast, unseen tapestry of paradox. The first clue that our celestial cartography is riddled with errors. We've been too confident to see. Before we descend further into this existential vortex, we must anchor ourselves in the specific, meticulous claim at the heart of the cataclysm. The staggering mass discrepancy, that factor of 120, is merely the screaming symptom, the fever spike. The true pathogen, the engine of this mystery, is hiding in a deceptively simple concept, non-gravitational acceleration. And to understand that force and why its measurement has spawned this chaos is to take the first real step into the heart of the strangeness. If this unfolding paradox pulls at you, if you feel that ancient human urge to stare into the unknown and demand an answer, then I want you with me for every step of this deep dive. Go ahead and subscribe. Stay in the loop as we dissect this mystery layer by layer, from the meticulous observations to the wildest implications. And leave a comment. Tell me where on this planet you're joining this investigation from. What time zone finds you pondering interstellar mysteries? And give me your first instinct. Do you think the solution is already hidden in the data? Or is 3i Atlas guarding a secret we haven't even learned how to question yet? The paper that ignited this crisis carries a deceptively mundane title, the kind only another specialist would glance at twice. Its authors, Forbes and Butler, are not provocateurs but meticulous astronomers, and their analysis, published on December 20, 2025, followed every norm of academic rigor. In the ordinary flow of science, it should have been absorbed, slowly discussed in seminars, critiqued in peer review, its conclusions gradually integrated or dismissed. It did not follow that pattern, because nestled within its complex equations and tables of data was a single measurement that acted like a philosophical grenade, rolling silently into the heart of our assumptions about 3i Atlas and refusing to cooperate with any of them. That measurement is known as non-gravitational acceleration, or NGA. The term sounds exotic, but the principle is straightforward. When you track an object through the solar system, you expect it to follow a path dictated solely by gravity, the relentless pull of the sun, modified by the gentler tugs of planets. With perfect knowledge of masses and positions, you can predict its location years into the future with astonishing precision. Yet sometimes, especially with comets, the object drifts. It ends up slightly, measurably off course, as if given a faint, extra nudge. That nudge is non-gravitational acceleration. For comets, the culprit is almost always outgassing. As ice is on the comet's sun-warmed surface vaporized, the jets of escaping gas act like tiny, asymmetric rocket engines. Newton's third law is immutable. For every action, an equal and opposite reaction. The gas blasts out in one direction, the comet gets a minute push in the other. Over weeks and months, this gentle, persistent thrust can alter a trajectory in ways pure gravity cannot explain. Forbes and Butler, using a global network of radio telescopes to track 3i Atlas with pinpoint accuracy in December, measured this effect. They quantified the push. The value they obtained was 89.3 × 10⁹ astronomical units per day squared. To the human mind, that number is meaningless abstraction. Let me translate it. Imagine 3i Atlas coasting through the void. Every single day, due to this outgassing push, it picks up an additional 13 kilometers per hour of speed. 13 kilometers per hour is slower than a bicycle, but space is a vacuum, and time is endless. A tiny acceleration, uncompensated and unopposed, compounds relentlessly. Over a week, that's a noticeable drift. Over a month, it becomes a major orbital discrepancy. It is the gentlest of whispers that, given enough silence, grows into a shout the universe cannot ignore. This is where the Forbes and Butler paper moved from observation to profound implication. They didn't just measure the push, they sought its source, and here, they deployed the most powerful tool in the history of astronomy. The James Webb Space Telescope. Specifically, they used data from its NISPEC instrument, which can dissect the infrared light from the comet into a chemical barcode. JWST didn't just confirm outgassing, it quantified it with brutal precision. The data showed 3i Atlas was losing about 150 kilograms of material every second, a substantial, roaring torrent of gas. Furthermore, JWST could estimate the velocity of that escaping gas, roughly 1,600 kilometers per hour. This is the critical parameter. In rocketry, exhaust velocity is everything. The faster the propellant is expelled, the greater the thrust it generates. So 150 kilograms jetting away at 1,600 kilometers each translates into a specific calculable force acting upon the nucleus. So far, this is classic comet physics, a textbook case. Outgassing produces force. Force produces acceleration. Acceleration changes the orbit. This is the dance we've understood since Halley, but then comes the devastatingly simple math, the step that detonated the consensus. The acceleration of any object is given by the most foundational equation in dynamics. Force equals mass times acceleration, or rearranged. Acceleration equals force divided by mass. It's the same principle that tells you a shopping cart full of bricks is harder to push than an empty one. Forbes and Butler had just measured the acceleration, the push, with their radio telescopes. They had just calculated the force, the thrust, from the JWST outgassing data. Only one variable remained: mass. Plugging their numbers in, the equation spat out an answer: 260 billion kilograms. The result was internally flawless, a closed loop of consistent physics. The observed acceleration perfectly matched the force expected from the observed outgassing, which in turn implied a specific, lightweight mass. The pieces locked together with satisfying logical clicks. The physics checked out. This was not sloppy work. It was a masterclass in remote measurement. It presented a coherent, evidence-based portrait of 3I Atlas as an actively outgassing, relatively lightweight comet, maybe a kilometer across, getting noticeably shoved around by its own vapors. It was a solved mystery, except for everything that came before December, because if this portrait is true, if 3I Atlas is really this lightweight reactive pebble, then the object's entire 5-month passage through the inner solar system prior to December becomes an inexplicable phantom. Earlier, when it was closer to the sun and solar heating was more intense, outgassing should have been stronger, not weaker. The forces should have been greater. The resulting non-gravitational acceleration should have been more obvious, not less. The trajectory should have been a mess of tiny deviations, a path impossible to reconcile with gravity alone. Yet for those 5 months, that is not what happened, not even close. Hundreds of telescopes were watching, and they saw nothing. Pure, ballistic, gravitational motion. The object moved as if it were in a perfect vacuum, responding only to gravity, utterly indifferent to the torrent of gas that, according to December's snapshot, must have been blasting from its surface. Thus, the paradox crystallizes with unbearable sharpness. The December data is not an outlier, it is a self-consistent system. The JWST saw the gas. The radio telescopes measured the push. The math demands the low mass. You cannot reject one piece without rejecting the exquisite harmony of all three, yet to accept them is to indict the 5 months of prior observation as either grossly incompetent or somehow blind to a force that should have been dominating the object's motion. We are left with two mutually exclusive truths, each supported by impeccable evidence, each describing a different universe. In one universe, 3I Atlas is a massive, stable giant that coasted silently. In the other, it is a fragile, reactive comet that shouted its presence in every metric. Both universes cannot be true for the same object obeying the same laws of physics, but the data from both exists, solid and unyielding. This is the standoff, and before we can even begin to resolve it, we must examine the other side of the contradiction with the same forensic intensity. We must go back to those 5 months of perfect, impossible silence, between March and August of 2025, before the Forbes and Butler paper was a draft, before the paradox had a name. 3I Atlas became the most precisely tracked object of its kind in history. The effort was not born from a premonition of strangeness, but from a simple, powerful scientific desire to see if anything at all, was happening beyond gravity. The campaign was led by astronomers Quach and Veris, and it represented a monumental feat of coordination. They marshaled over 230 observatories across the globe, from high-altitude desert sites to remote island outposts, all training their optics on that single faint point of light. This was not casual stargazing. This was astrometry at the bleeding edge of what is possible from Earth's surface, an obsessive pursuit of precision. Their goal was deceptively simple: to measure the position of 3I Atlas against the background stars with such insane accuracy that even the most minuscule deviation from a purely gravitational path would be revealed. We are talking about tracking positional changes down to 0.2 arcseconds. To grasp this, understand that an arcsecond is 1/3600 of a degree. It is the angular size of a dime viewed from about 4 kilometers away. The Coy-Varis campaign was measuring shifts 36 times smaller than that. It is the equivalent of watching someone place a coin on the ground from 100 kilometers away and being able to tell if they nudged it half a centimeter to the left. This is the realm of the fantastically small, where the twinkle of Earth's atmosphere is the enemy and statistical noise is a constant war. They built not a snapshot, but a narrative. For 5 continuous months, they gathered data points, each one a tiny dot in the sky, each one cross-checked, calibrated, and refined. They were constructing an orbital solution of unprecedented fidelity, a digital ghost of the object's path so precise it could feel the faintest breath of a non-gravitational force. Outgassing doesn't announce itself with a violent jerk. It manifests as a slow, steady drift, a residual that accumulates day by day as the object fails by microscopic amounts to be where gravity says it should be. The CLA team's entire apparatus was a seismograph built to detect that specific quiet tremor in the orbit. After 5 months, after petabytes of data and countless hours of analysis, they published their result. They had found the tremor, the drift, the signature of forces beyond gravity. They found nothing. Absolute, unequivocal null, 3I Atlas. For the entire duration of the campaign, moved with a precision that matched a purely gravitational model to within the infinitesimal noise floor of their measurements. Every observation, every single one of the hundreds of data points, fit the curve of an object being tugged only by the sun and planets. There was no drift, no deviation, no whisper of an extra push. For 5 months, this object coasted through the violent thermal and radiative environment of the inner solar system like a bullet in a vacuum, a perfectly ballistic projectile. It showed all the dynamic character of a cannonball. Now, the immediate, reasonable objection is, perhaps the non-gravitational forces were simply too small for even this exquisite experiment to detect. This is where the CLA team's work becomes of use, tightening the paradox to its most painful point. They didn't just take data, they calculated their own detection threshold. They knew to a mathematical certainty exactly how sensitive their net was, and according to their published analysis, their campaign could have detected a non-gravitational acceleration signal 300 times weaker than the robust 89.3 9.3 sex 1090 day squared that Forbes and Butler measured in December. Read that again, 300 times weaker. Let it sink in. The December signal was not subtle or borderline. If that level of acceleration had been present during the CLA campaign, it would not have been a faint blip needing sophisticated extraction. It would have screamed through their data. It would have been the most obvious feature in their orbital residuals. A signal so loud it would have been impossible to miss, like a trumpet blast in a silent room. And yet, their data was silent. The signal was not there. It was absent, not because their instruments were insensitive, but because the phenomenon itself was absent. The contradiction is now geometrically precise and horrifying. We have 2 observational epochs. In Epoch 1, March-August, a maximally sensitive search finds 0 acceleration, constraining any force to be less than 1/300th of the December value. In Epoch 2, December, a direct measurement finds a large, unambiguous acceleration. The object was closer to the Sun, and thus presumably hotter and more active during Epoch 1. Cometary activity does not switch on like a light bulb. It is a smooth function of solar heating. So, the silence of Epoch 1 is not just a non-detection. It is a positive detection of stability. It tells us something profound about the object's nature during that time. It was behaving as an object with immense inertia. Because inertia, the resistance to changes in motion, is mass. If you push on a shopping cart and it doesn't move, you infer it's full, heavy. The CLA data, by showing no response to the presumed pushing force of outgassing, implicitly measured a high mass. It said, this object is too heavy to be budged by these forces. But then, December arrives, and suddenly, the same object, according to Forbes and Butler, is leaping to the push of outgassing like a lightweight craft, its low mass laid bare by its own reactivity. Same object, same laws of physics, 2 diametrically opposed inertial responses. This is no longer about conflicting mass estimates. It is about conflicting realities. The CLA team saw a boulder, immovable. Forbes and Butler saw a beach ball, tossed by the wind. Both teams are respected. Both methodologies are sound. Both datasets are public. This is not bad science. This is reality refusing to conform to our models, and the refusal centers on that most fundamental property, inertia. To understand the depth of this crisis, we must now isolate and examine this core problem, because it threatens not just a comet's profile, but a cornerstone of physics itself. Inertia is the ghost in the machine of motion. It is the reason you feel pressed into your seat when a car accelerates, or lurch forward when it brakes. It is the tacit resistance of matter to any change in its velocity. More formally, It is the manifestation of mass in Newton's second law, F equals ma. For a given force, F, the resulting acceleration, a, is inversely proportional to the mass m. A small mass accelerates quickly. A large mass accelerates sluggishly. This is not a theory or a model. It is the bedrock of classical mechanics, the equation we've used to land on Mars and predict eclipses for centuries, and it provides the cleanest, most direct way to weigh something in space without a scale, apply a known force, measure the acceleration, and solve for mass. For 3I Atlas, astronomers weren't actively pushing it. Instead, they were passive observers, watching how it responded to the natural forces of its environment. The primary suspected force was outgassing thrust. The CLI campaign's null result is a measurement of acceleration. They measured an acceleration statistically indistinguishable from zero. This means, within the limits of their incredible sensitivity, the force from outgassing divided by the mass yielded approximately zero. The only way for that equation to hold is if either the force was zero or the mass was effectively infinite, since we have direct spectroscopic proof from later that outgassing was occurring. The simplest, most forceful conclusion from the clawed data is that the mass was simply too large for the outgassing, forced to produce a measurable acceleration. It was the cosmic shopping cart full of bricks. The Forbes and Butler result is the inverse. They measured a specific, significant acceleration and derived the specific force causing it from JWST data. Their equation, A equals FF/m, gave them a small m. It was the empty shopping cart. The paradox is now stripped to its mathematical bones. The two experiments both measured A acceleration. They both, through different means, estimated F force. They solved for m and got answers that differ by a factor of 120. The equations themselves are in conflict. One might look for escape hatches in the other variables. Could the force have been miscalculated? JWST's measurements of outgassing rate and gas velocity are state-of-the-art, but they rely on models of cometary chemistry and emission. Perhaps, but to bridge a factor of 120, you'd need to be wrong by 2 orders of magnitude about the gas production or its speed and error bar, far outside what JWST's precision allows. Could the acceleration have been miscalculated? Orbital determination is a complex art, but both teams are masters of it. The claim on detection is particularly hard to wave away because it's not a positive number with error bars that overlap zero. It's a stringent upper limit. They didn't get a fuzzy small number. They got nothing here, with a threshold so low it excludes the December signal by a vast margin. This leads to the chilling heart of the inertia problem. Inertial mass is not some abstract property we infer from brightness or color. It is defined by an object's dynamical response. The CLI data defines 3I, Atlas, operationally, as an object with high inertial mass. The Forbes and Butler data defines it, in the same operational terms, as an object with low inertial mass. Physics dictates that inertial mass is a constant, intrinsic property. An object cannot have 2 different inertias, any more than a ruler can have 2 different lengths. The equivalence of inertial and gravitational mass is the foundation of Einstein's general relativity, tested to phenomenal precision. If 3I Atlas is somehow violating this, we are not looking at a strange comet. We are looking at a revolution in fundamental physics. Before we make that breathtaking leap, we must exhaust every possible mundane explanation. Perhaps shape and rotation are conspiring to hide the truth. A cigar-shaped tumbling object could have complex outgassing patterns. Maybe jets on opposite sides fire at different times in its rotation, cancelling out the net thrust on average. But the CLI campaign lasted for 5 months, countless rotations. For cancellation to be perfect, averaged over that time, to within 1/300th the December force, requires a geometric and temporal coordination so precise it beggars belief. It asks for a perfect, sustained symmetry in an object known to be asymmetric and evolving. Or perhaps the object's brightness fooled us about its size, and thus the mass we inferred in the early, giant model. But inertia doesn't care about brightness. A small shiny object and a large dark one can reflect the same light, but if you push them with the same force, they will accelerate differently. The claw data was a direct push test. It didn't measure light, it measured motion. It said, this thing, whatever its size or color, does not move easily. We are cornered by the equation. A equals F/m. To reconcile the two results, one of those 3 letters must be a variable we don't understand. It could be non-constant, but that would mean the object's acceleration changed dramatically between August and December, which brings us back to the question of why. F could be non-constant, but the force should have been stronger earlier, not absent. I'm could be non-constant, but how does an object lose 99% of its mass in a few months without showing a single visible sign of doing so? This last question forces us to confront the most dramatic of the natural explanations, that 3i Atlas simply shed an almost incomprehensible amount of material. To see if this is even remotely plausible, we must venture into the violent, messy world of comet death and see just how completely standard comet logic shatters against this mystery. Part 5. The Impossible Comet. Let's perform a simple subtraction, a calculation that highlights the sheer absurdity of the mass loss explanation. The old estimate, 33 trillion kilograms. The new estimate, 260 billion kilograms. The difference is roughly 32.7 trillion kilograms. That is the amount of mass that would have had to vanish, sublimate, explode, crumble into dust from 3i Atlas between the Claude observations and the Forbes and Butler measurements to make both numbers sequentially true for the same object. 32.7 trillion kilograms. It is not a slight weight loss. It is not even a catastrophic diet. It is a metaphysical evaporation. It is the equivalent of the object discarding 99.2% of its very substance. Now, comets lose mass. It is their defining activity. They are dirty snowballs, and when the sun heats them, the ices turn to gas and blow away, dragging dust with them. We have seen it for centuries. A very active comet might shed millions, even billions of kilograms per orbit. But 32.7 trillion? In a matter of months? The scale is so ludicrous it crosses from astronomy into farce. To lose that much mass that quickly is not to be a comet, it is to be an explosion in slow motion. And explosions are not subtle. When a comet undergoes a major fragmentation event like Comet Schwarzmann-Volkmann 3, or the progenitor of the Kreutz grazers, it is a spectacular astronomical event. The brightness spikes by orders of magnitude as fresh, pristine ice is exposed to sunlight. A massive expanding cloud of debris forms. The comet's tail becomes a brilliant, chaotic plume. It makes headlines. Every telescope, from professional behemoths to backyard instruments, turns to watch the show. The universe announces it with a flare of light. 3i Atlas did none of that. Its light curve was stable. Its appearance in telescopes remained a star-like point. There was no great debris cloud, no sudden cometary outburst, no secondary fragments detected drifting away. It was, by all visible accounts, a coherent, stable body. It behaved exactly as a solid, intact object should, not as something in the terminal throes of self-immolation. You cannot quietly vaporize 99% of a mountain. The energy required alone would be staggering, and the luminous signature of that much sublimating gas and ejected dust would have been the brightest thing in its region of the sky. But the sky was dark. The object was quiet. This forces us to consider exotic chemistry. Maybe 3i Atlas isn't made of familiar water and CO2 ice. Maybe it's composed of hypervolatile ices that sublimate far more efficiently. Something exotic from an alien protoplanetary disk. Hydrogen cyanide was detected. A hint of strangeness, but volatility is only half the equation. It explains how mass could leave quickly, but not where it goes. 32 trillion kilograms of gas and dust, even exotic gas, does not disappear. It forms an immense coma, a glowing shroud around the nucleus that scatters sunlight. It creates incredibly strong emission lines in spectra. JWST would have seen not just outgassing, but an object utterly shrouded in its own catastrophic eruption. The modest outgassing signatures it did detect are orders of magnitude too small to account for such Armageddon. Then there is the structural problem. An object that loses 99% of its mass is not gently shrinking. It is disintegrating. Its gravitational self-binding energy is overcome. It flies apart. We have watched comets like Shoemaker-Levy 9 do this under Jupiter's tidal pull, splitting into an iconic string of pearls. A disintegration on the scale required for 3i Atlas would have produced not one, but dozens or hundreds of detectable fragments, a cloud of debris that would have persisted for years. Yet, after December, observers tracking the object saw a single nucleus, coherent, whole. Standard comet physics in every form hits a wall. The quiet behavior rules out massive, continuous mass loss. The lack of a debris field rules out catastrophic fragmentation. The modest outgassing seen rules out hypervolatile-driven evaporation at the required scale. The numbers do not just fail to add up. They describe a sequence of events that is physically nonsensical. 3i Atlas did not behave like a comet undergoing any known process. It maintained the structural integrity of a giant, while allegedly possessing the mass of a pebble, and it transitioned between these states without the violent luminous upheaval that must accompany such a transformation. This is the point where the paradox ceases to be a measurement error and becomes a genuine ontological crisis. We have ruled out the obvious. It is not a simple mistake. It is not normal cometary behavior. Even extreme normal behavior. The object is violating a sequence of expectations that are deeply entrenched. When you eliminate the impossible, whatever remains, however improbable, must be the truth. But before we reach for the profoundly improbable, science must try to engineer a rescue. It must attempt to build a bridge between the two datasets using only known physics, even if that bridge is made of gossamer and coincidence. This is the work of the next phase, constructing the elaborate, fragile edifice of natural explanations that might, just might, hold this paradox together without breaking. Faced with the impossible comet, the scientific mind begins to architect escapes. These are not admissions of defeat, but creative exercises in applying known physics in extreme combinations. The first and most elegant of these escape hatches is the concept of vector cancellation. Imagine a child on a skateboard holding two fire extinguishers, one pointed forward, one backward. If they pull both triggers at once, the equal and opposite thrusts cancel. The child goes nowhere despite both engines firing at full blast. Now translate that to a comet. What if, during the 5 months of the Cly campaign, 3i Atlas was outgassing vigorously, but its jets were arranged in a perfect symmetrical geometry? If active regions on opposite hemispheres fired with equal force, the net thrust could sum to zero. The comet would be a roaring engine going precisely nowhere, perfectly mimicking ballistic motion. It is a beautiful, intellectually satisfying idea. Comets are not uniform. Their surfaces are patchworks of ice and rock. As they rotate, different patches heat up and activate. Could the pattern of active regions have conspired to produce perfect cancellation? Theoretically, yes, but the Clay data raises the bar from possible to miraculous. Remember, they could have detected a force 300 times weaker than the December value. For cancellation to hide the signal, it wouldn't need to be rough or approximate. It would need to be perfect within 1 part in 300. Not mostly balanced, but perfectly balanced, across hundreds of observations, over 5 months of changing solar angles and thermal conditions. The comet's rotation, the precise locations of the vents, their individual outgassing rates all would have to be exquisitely tuned in a sustained dance of equilibrium. It asks for a temporal and geometric coincidence of staggering precision. And then, for the story to hold, this perfect balance must have broken precisely by December, when Forbes and Butler were looking. Perhaps one major vent froze over or exhausted its volatiles. Perhaps thermal precession, a real effect where outgassing torques alter a comet's spin, slowly rotated the object into a new orientation, where the force is no longer cancelled. This adds another layer of just so timing. The object maintains a flawless silent symmetry for the exact duration of a world-class observation campaign, only to conveniently become lopsided and reveal its thrust just in time for another world-class campaign to measure it. The universe is under no obligation to be convenient, and stacking such specific timing onto already precise geometry strains credibility. The second major rescue attempt is the thermal lag model, championed by researcher T. Marshall Eubanks. This model leverages a simple fact. Heat takes time to travel. Put a frozen turkey in the oven. The skin burns before the center thaws. A comet is a poor conductor. Sunlight heats the surface immediately, but that heat wave propagates inward slowly over weeks or months. Eubanks proposes that during the Clog campaign, only the surface layers of 3i Atlas were warm enough to outgas. This outgassing was weak, diffuse, and perhaps symmetrical enough to explain the lack of a net push. However, all that while, solar heat was seeping deeper. By December, the thermal wave finally reached volatile-rich pockets buried in the interior. These deep reserves then activated explosively, causing the strong asymmetric outgashing that Forbes and Butler measured. This model has strong merits. It is based on solid physics. It explains the timing, why strong activity might suddenly appear months after perihelion. It provides a natural trigger for the transition from silence to shout. It feels satisfyingly physical, but it runs aground on the same rock as before, inertia. Thermal lag explains when the engine turns on, but it doesn't explain the weight of the vehicle. Even weak, symmetrical outgassing during the clock campaign would still involve force acting on mass. If the true mass is as low as 260 billion kilograms, even that weak cancelling force would have produced some residual wobble, some tiny deviation well above the Klein detection threshold. The clay data doesn't just say the engine was off. It says the vehicle is so heavy that the tiny engines we can infer couldn't move it. Thermal lag can delay the big thrust, but it cannot make a lightweight object pretend to be heavy. To survive, the Eubanks model must ally itself with another idea, that the density, and thus the mass implied by a given size, is wrong. Which brings us to the workhorse of astronomical reconciliation: density. Our assumption of 500 kilograms was MJ for 3I Atlas is a direct import from solar system comets. But what if interstellar comets are different? What if, forged in a different stellar crucible, they are made of denser, more compact material? If the density is 1500 kilograms/Mach, the mass for a given size triples. Suddenly, the old giant estimate could be produced by a smaller, denser object, and the December mass estimate might be higher too, if the outgassing is acting on a denser, smaller nucleus. Perhaps the truth lies in a middle ground, a dense few trillion Kidri object that can resist weak forces but still respond noticeably to strong ones. Density is the parameter doing heroic, unpaid labor in the background of this mystery. It is the universal fudge factor. But it is also a confession of ignorance. We have no direct measurement of density for any interstellar object. Invoking it doesn't solve the paradox. It merely moves the goalposts of the unknown. It highlights that every link in our inference chain, brightness to size, size to volume, volume to mass, is coupled to an assumption. Change the assumption of homogeneity, and the chain unravels. We are left with the unsettling realization: our models are flexible enough to accommodate almost any outcome by tweaking these hidden parameters. A model that can explain anything risks explaining nothing. It loses predictive power. We are, in effect, adding epicycles not to an Earth-centered universe, but to a comfortingly familiar, solar system-centered understanding of what comets are. The coincidences are piling up: perfect geometry, fortuitous thermal timing, convenient density. Each rescue is plausible alone. Together, they form a narrative of staggering, unsustainable luck. And when natural explanations begin to require a conspiracy of low-probability events, it is time to step back and ask a dangerous, thrilling question. Are we solving the right puzzle, or is the very category of comet the wrong box for this thing? As astronomers wrestled with geometry, thermal lags, and the phantom of density, the ground beneath their feet was quietly moving. The paradox of 3I Atlas was not playing out in a static arena of fixed numbers, but in the fluid, iterative world of orbital mechanics, where certainty is a process, not a destination. This layer of the mystery, the moving target problem, complicates everything and reveals the messy human reality of science at its frontier. The central repository for tracking solar system objects is NASA's Jet Propulsion Laboratory Horizon System. It is the oracle that mission planners and astronomers consult to know where an object is, was, and will be. Its models are constantly updated as new data flows in. For a newly discovered, fast-moving interstellar visitor like 3I Atlas, the early orbital solutions are labeled provisional. This is a technical term with profound implications. It means the numbers have wide error bars. The model is a sketch, not a blueprint. Key parameters, especially subtle ones, like non-gravitational acceleration, NGA, are poorly constrained and can swing significantly with each new batch of observations. In the early months, JPL's model for 3I Atlas included a small, tentative NGA term. It was a placeholder, acknowledgement that something might be pushing it. As the CLE team's exquisite data streamed in, that term likely shrank, converging toward the zero their analysis found. Then, when Forbes and Butler published their December measurement of a robust acceleration, JPL would have had to incorporate that, causing the parameter to jump. For the public, and even for many scientists not intimately tracking the daily database updates, the narrative froze at the last dramatic headline: object loses 99% of its mass. But in the Background: the Oracle was whispering revised numbers, adjusting error margins, shifting the foundation upon which the mass estimates were built. This is the moving target problem in its purest form. Forbes and Butler's stunning mass calculation depended critically on the exact value of the non-gravitational acceleration they used. That value was itself a snapshot from a dynamical model that was, and still is, evolving. If the official NGA estimate from JPL later shifted by even 20%, a routine occurrence as an orbit is refined, the inferred mass would shift by a corresponding amount. The 260 billion kilogramming is not a timeless fact carved in stone. It is a conclusion drawn from a specific temporal state of a living database. The same applies to the earlier giant mass estimate. It, too, was built on a provisional model, one that likely assumed a density and size that were themselves best guesses. This constant, quiet revision isn't a scandal. It is how science works. It is the process of convergence. You start with a blurry picture and a rough guess. You collect more pixels. You sharpen. You realize your first guess about what the blur represented was wrong. You update. The goal is not to be right on the first try, but to relentlessly pursue a consistency that finally locks the picture into focus. The problem is one of communication and perception. The initial dramatic story of the 5-kilometer giant achieves narrative escape velocity. It leaves the cautious, qualified world of academia and enters the public consciousness as fact. The subsequent corrective updates, the quiet tweaks to the JPL ephemeris, the papers arguing for a denser composition are less sexy. They don't make headlines. The public is left with an outdated understanding, while scientists are already 5 steps ahead, arguing over the implications of the third decimal place in a parameter that has already changed. This gap between the lived process of science and the perceived product of science is where 3i Atlas teaches a crucial, humbling lesson. We crave the clean story, discovery, confirmation, conclusion, but reality is a tangled web of iterative modeling, stacked uncertainties, and evolving consensus. The mass paradox might, in part, be an artifact of this process, a collision between two confident-sounding snapshots taken at different stages of the model's maturation. Perhaps, as the orbit solidifies over years of analysis, the NGA estimates from the two epochs will converge, or one will be shown to be a misinterpretation. The gap of 120 might shrink to a factor of 10, then 3, then into overlapping error bars. The paradox would dissolve into ordinary scientific refinement, but there is a darker, more thrilling possibility. What if, after all the data is in, after every orbital parameter is squeezed dry of uncertainty, the gap remains? What if you achieve perfect precision on the acceleration measurements and the force calculations, and the two masses they imply are still irreconcilable? You reach a threshold where improving the data no longer reduces the tension. It only makes the contradiction more precise, more undeniable. This is the threshold of genuine anomaly. 3i Atlas is pushing us toward that cliff, and standing at that cliff, we are forced to look beyond the everyday variables of density and orbital models, and confront a tool that is reshaping our entire view of the small body population. The James Webb Space Telescope, JWST, was not built for comets, but it is for them a revolutionary instrument. Its infrared eyes are so sensitive they are detecting chemistry and physics that were previously invisible. For 3i Atlas, it didn't just see outgassing. It identified specific molecules like hydrogen cyanide at abundances that raised eyebrows. But this is part of a broader, quiet revolution. JWST is looking at asteroids and comets within our own solar system and finding that they too are strangers. Chemistry that shouldn't be there, thermal properties that don't match predictions, activity where none was expected. It is revealing that our textbook knowledge of small bodies was built on the brightest, easiest to study examples. We generalized from the exceptional to the norm. And now JWST is showing us that the norm is far more diverse, complex, and weird than we imagined. 3i Atlas, as an interstellar object, sits at the extreme edge of this newly revealed diversity. We have no baseline for normal in its class. Every assumption we import from our solar system about density, composition, thermal response is a guess. JWST data on 3i Atlas isn't just confusing in isolation. It is a data point in a new distribution curve we are only just drawing. The paradox, therefore, might not be that 3i Atlas is broken. The paradox might be that our categories are too small. The comet box built for solar system debris, might simply be the wrong shape for objects forged in alien stellar forges, when your only sample of interstellar objects is two, and both are profoundly odd, Oumuamua and 3I Atlas. That perhaps the conclusion is not that they are freaks, but that our solar system's population is the freak. Or at least, not representative. This realization doesn't solve the inertia problem, but it recontextualizes it. We are not just trying to weigh one object, we are trying to decipher the rulebook for an entirely new league. Using a rulebook we wrote for a different game, there is a question that has lingered at the edge of this investigation since the first mention of Oumuamua, a hypothesis that moves uneasily in the shadows of conference halls and in the private thoughts of researchers. It is the hypothesis of artificiality. To be unequivocally clear, this is not a conclusion. It is not evidence. It is a speculative, low-probability possibility that persists for one stubborn reason. The data, thus far, has refused to rule it out cleanly, and in the case of 3I Atlas, the pattern that keeps this hypothesis alive has become uncomfortably familiar. Rewind to 2017, and Oumuamua, it was odd from the start. An extreme pancake-like shape, no visible coma or tail, a brightness curve unlike any asteroid, and then, the kicker, it exhibited non-gravitational acceleration with no visible outgassing. The natural explanations were strained. Maybe it was outgassing pure hydrogen, hard to see. Or maybe it was a solid nitrogen iceberg, exotic but possible. Maybe radiation pressure was enhanced by its shape, a stretch but calculable. Each required special just-so conditions. Then Harvard's Avi Loeb, in a carefully caveated paper, suggested the acceleration profile was consistent with a thin, light sail-like structure. He wasn't crying aliens. He was asking if, given the inadequacy of prosaic models, the hypothesis should at least be on the table for future such objects. The reaction was volcanic, a mix of scientific outrage and media sensationalism that drowned the nuanced question in noise. Now enter 3I Atlas. Different object, different specifics, but a hauntingly similar narrative arc. Phase 1. Extended period of ballistic, purely gravitational motion, cloy campaign. Phase 2. Sudden onset of measurable non-gravitational acceleration near perihelion, Forbes and Butler. For Oumuamua, the lack of outgassing was the key oddity. For 3I Atlas, it is the binary switch from heavy behavior to light behavior, without the cataclysmic physical transformation that should accompany it. Both stories feature a passive coasting phase followed by an active, propelled phase. In the terminology of spacecraft, this is ballistic flight followed by powered flight. The natural explanations for 3I Atlas as we built them are a precarious tower of coincidences. Perfect jet cancellation, perfectly timed thermal lag, conveniently unusual density, and cooperative rotation. Each plank in the tower is physically allowable. Together they construct a scenario of staggering, implausible luck. This does not make the artificial hypothesis correct. It simply highlights that our natural models to survive are being pushed into realms of extreme contingency. When your explanation requires nature to have arranged 5 low-probability events in a precise sequence, you are no longer applying Occam's razor. You are performing narrative acrobatics. The artificial hypothesis persists not because scientists believe it, but because of a logical asymmetry. You can disprove a specific natural model, e.g., it can't be water ice because we see no water lines, but it is notoriously difficult to disprove artificiality with remote sensing alone. Without intersecting the object, without touching it, you can only ever say, natural explanations of increasing complexity can account for the data. You cannot prove the absence of design. This makes the hypothesis scientifically frustrating. It's a conversation stopper, not a starter. It is untestable with current technology for an object already departing. Mentioning it invites ridicule and attracts the wrong kind of attention, which is why working scientists largely avoid it in formal discourse. Yet its spectral presence in the 3I Atlas story serves a vital purpose. It acts as a mirror, reflecting the limits of our current paradigms. When the only way to keep an object within the natural box is to inflate epicycle upon epicycle of special conditions, it forces a profound question. Is the box itself the problem? The artificial whisper is really just the loudest form of asking, what if this isn't a comet at all? What if we're trying to fit it into a category it was never meant to occupy? This is not an argument for aliens. It is an argument for radical open-mindedness about natural phenomena. Perhaps 3I Atlas represents a class of object that forms through processes unknown in our solar system processes, that create exotic internal structures or material properties. A hypothesis, in its most productive form, is a challenge to our terrestrial chauvinism. It forces us to consider that the universe might fabricate things that, to us, look engineered, simply because our experience is cosmically parochial. The most unsettling possibility is not that 3I Atlas is a spacecraft, but that it is a naturally occurring object that blatantly violates the engineering principles we thought governed small body formation. It would be a natural marvel so strange it impersonates artifice. This line of thinking leads inevitably away from surface features and into the interior. If we are to find a natural yet profoundly exotic explanation that resolves the inertia paradox, it likely lies not in what 3I Atlas is made of, but in how that material is arranged. We must confront the possibility that our fundamental assumption, that it is a homogeneous, solid lump, is the root of all our confusion. To solve this, we must venture into the realm of structural degeneracy and imagine what kind of internal architecture could make a single object behave like both a boulder and a balloon. Consider two objects with identical mass. The first is a solid sphere of granite, dense and uniform from core to crust. The second is a perfect hollow titanium shell, like a fantastically robust beach ball. From a distance, reflecting sunlight, they could appear identical. Their gravitational pull on a passing particle would be the same. Their total mass is the same, but their internal structure, and thus their response to certain forces, could be wildly different. This is the concept of structural degeneracy. Radically different internal configurations can produce identical external observables when viewed through the limited lenses of remote astronomy. We measure light, brightness, spectrum, and motion, orbit, acceleration. These things tell us about surface composition and total mass, but they are almost blind to what lies beneath. Everything between the surface and the center is a guess, an assumption of homogeneity. For 3I Atlas, this assumption may be the keystone of the entire paradox. What if 3I Atlas is not a homogeneous mix of ice and dust? What if it has a layered, anisotropic, or even hollow structure? Imagine a dense, rocky metallic shell, several meters thick, encasing a largely empty interior, or one filled with a porous, low-density filler like icy foam. This is not pure fantasy. We see structural efficiency everywhere in nature. Bird bones are hollow for lightness, diatom shells are intricate lattices, planets differentiate into dense cores and lighter crusts. Comet 67P, visited by Rosetta, was found to be incredibly porous, more void than solid. The leap to a shell-like structure is not immense. Now, apply this to the paradox. The Gaia campaign measured the object's response to diffuse forces, like weak averaged outgassing or solar radiation pressure. These forces act on the entire body. A shell structure with a given total mass would respond to these broad pushes, just like a solid body of the same mass. Its inertia, its resistance to being moved, would be defined by its total mass. Hence, it would coast ballistically, showing no deviation. It would behave like the giant. Now, consider the Forbes and Butler December measurement. They measured a strong localized force, outgassing jets from specific patches on the surface. This is where structure matters profoundly. If the outgassing is erupting from a relatively thin, rigid shell, the dynamics change. The thrust is not pushing against the entire, distributed mass of a solid sphere. It is pushing against the localized mass and rigidity of the shell at that point. Think of it like pushing on an empty soda can versus a solid steel cylinder of the same weight. A finger can dent the can and set it rolling with ease. The cylinder barely moves. The shell could be much more responsive to localized thrust than a homogeneous body of identical total mass. The measured acceleration could be larger, implying a lower effective mass in that specific force equation, even if the total mass is high. This hypothesis elegantly bridges the two realities. The high total mass, suggested by the Claw-Null result, gives the object the high inertia to ignore weak, averaged forces. The thin shell response, observed by Forbes and Butler, allows it to react strongly to localized jet forces, yielding an apparently low mass from the F=ma calculation. Both data sets are correct. They're measuring different aspects of the same, structurally complex object. The paradox dissolves not by changing physics, but by changing our mental picture from a simple snowball to a complex engineered-looking natural artifact. It is a compelling narrative. It requires no new physics, only an abandonment of the homogeneity assumption. It explains the silence, then the shout, but here lies the rub. The reason this remains a hypothesis and not a solution: we cannot test it. Our telescopes are photons. They see surfaces. We have no X-ray vision for asteroids. To probe interior structure requires techniques we did not and could not deploy on 3I Atlas. Radar tomography from a nearby spacecraft, seismic monitoring from a lander, precise gravitational mapping by an orbiting probe. By the time we realized we needed these data, 3I Atlas was already a fading speck in the outer darkness. So, the shell hypothesis, like the artificial one, sits in a purgatory of plausibility. It fits the data beautifully without invoking magic or miracles, only a more exotic form of natural complexity, but it is currently unfalsifiable. It turns 3I Atlas from a paradox into a lesson about the limits of observation. We are forced to admit that for all our technological might, we are still essentially cave dwellers watching shadows on a wall, inferring the shapes of things from silhouettes. We measured a silhouette of mass from inertia, and a silhouette of structure from localized acceleration, and they conflicted because we assumed the object casting the shadow was simple. The solution may be that the object is complex in a way we couldn't see. This is the ultimate humbling. The mystery of 3I Atlas may not be a puzzle we failed to solve. It may be a puzzle we never had the pieces to solve in the first place. The data we collected, for all its precision, was fundamentally incomplete. It told us that something was wrong, but it cannot tell us what. The object has become a permanent question mark, a monument to our ignorance, and in that role it teaches its most important lesson. So, what do we actually know about 3I Atlas? We know it came from beyond our solar system. We know it passed through in 2025, made a turn around the sun and left. We know multiple top-tier teams observed it with the best tools in human history. We know it outgassed. We know its basic trajectory. That is the bedrock. What don't we know? Almost everything else. Its true mass, size, density, composition, structure, and the reason for its bizarre dynamic shift are all shrouded in a fog of inference, assumption, and contradiction. The mass paradox is not an established fact. It is a symptom of this profound ignorance. We have two precise measurements that disagree, and no present way to adjudicate between them, because each is tied to a chain of assumptions that we cannot verify. This is not a failure of science. This is science. Science is not a vault of answers. It is a discipline of asking better questions in the face of acknowledged ignorance. The story of 3I Atlas is not a story of experts getting it wrong. It is a story of the process working exactly as it should. A bold initial estimate, contradictory new data, a period of chaotic re-evaluation, and the slow, grinding pursuit of a new consensus that may take years or decades to form if it ever does. The public often sees the first and last steps, the dramatic discovery headline, and the eventual textbook conclusion. 3I Atlas traps us in the messy, glorious middle. It exposes the gap between the clean narrative of popular science and the chaotic, iterative, uncertainty-filled reality of research. It teaches humility. We must learn to distinguish between what we have measured, photon counts, positional pixels, and what we have inferred, mass, density, structure. The former is hard data. The latter is a story we tell to make sense of the data, a story built on assumptions imported from other, possibly irrelevant contexts. 3I Atlas challenges our categories. Comet may be a label of convenience, not a fundamental truth. It reminds us that our solar system is a single data point, and that the galaxy is under no obligation to fill itself with copies of our local debris. The next interstellar visitor might be stranger still. This object is a preview of a future where we will repeatedly encounter the unfamiliar, and our comfortingly familiar models will buckle under the strain. Will the paradox be solved? Perhaps. A future analysis might find a subtle error in the timing of the Clyde data, or a misinterpretation of the JWST spectra. The masses might converge, or it might join Oumuamua as a permanent enigma, a classic cold case in astronomy that generates PhD theses for generations. Both outcomes are valid. Not every mystery gets a clean ending. What matters is that we looked, that we pointed our telescopes and marshaled our intellects to stare down the unknown. 3i. Atlas crossed our skies and, in its passing, did not give us answers. It gave us a better question. How do we understand that which is fundamentally alien to our experience? It pushed the horizon of our knowledge further away, reminding us that the frontier is not a line we cross, but a horizon that recedes forever. Every answer begets new questions. Every solved paradox reveals deeper mysteries. This isn't frustration, it is the engine of wonder. 3i Atlas is gone, but the next visitor is already out there, traveling the dark between stars, carrying its own secrets, waiting to challenge us again. And we will be here, watching, waiting to learn how much we still have left to learn.